All right, so we're going to take a look at 9.2, patterns in a table of values. Couple things here. Mostly it's pretty straightforward stuff. In this case, we're doing real simple, just calling it A and B. Convention is the first column that we've got always goes on the bottom of the graph, and so horizontally across the bottom, and the second column goes up the side. So there we go. If I was to graph, because that's kind of my first step, that's what part A up there says, graph the start. And again, these numbers go underneath the lines, not in the spaces. So 0, 1, 2, 3, 4. That's as far as my graph goes, so that's all I'm going to worry about. And then going up the side, so that's A. So I'm going to label this as A. That is not a very pretty A. Normally that should go underneath, and I didn't leave enough room because the 4 got rather big. Anyways, now going up the side, again, it's next to the lines, not in the spaces. So 0. We're going to count by 3s because that's what's going on here. 3, 6, 9, 12. All right, again, I guess I could have continued, right? 5, 6, 7, 8 down at the bottom, 12, 15, 18, 21 off the side. I don't need to, so I'm going to plot my points, put a dot. Good to get into a habit, and this is more from my teaching high school sciences. When you're making a graph, plot your point, and you can put a circle around it. It's a good way, especially now in this case, it is exact points, so we don't need to do that. But especially if you're having to estimate exactly where the point might be, that's a good practice to get into. So if you put circles around them, also means later on when you go to join the points, it just looks neater, and you know where your points are. All right, so let's circle around here, circle around here. Here's my point, put a circle around it. Here's my point. In this case, it's actually really easy. Put a circle around it, right? I guess I could look this one up and say, okay, well, 4 goes with 12, so 4 all the way up to 12, right? And if I go back and look at these other points, again, I sort of assumed you were going to be graphing them and knew how to graph them, but if you want a quick refresher, remember the first one, well, we go across to 0, up to 0, across to 1, up to 3, across to 2, up to 6, across to 3, up to 9, and so on. Now, I am not going to join these with a line on the screen because it's not going to be a straight line. It should be, but it wouldn't. So there we go. All right. Difference in consecutive A values. So what is the difference in value for consecutive A values? So from 1 to the next. Well, 1 to the next goes up by 1. So difference in consecutive A values is 1. Difference in consecutive B values is 3. All right. Describe in words the relationship between the values for A and B. So here's where we start to look at, okay, well, I'm going to have to scroll down here a little bit so you can. When A increases by what, B increases by 3. So in this case, when A goes up by 1, B goes up by 3. All right. Then each B coordinate is 3 times its A coordinate. An expression for B then is, so right, if we look at this, to get from A to B, that's another way of saying this, we're multiplying by 3. Okay, and so an expression for B then would be that B equals 3A. Right, that would be our expression for B. So actually that is the equation. The expression for B would be simply just 3A. All right. And that's really what we're getting at here with this. So let's take a look here. We can use a table actually to determine a linear relation. So if we look here, table 1, the x coordinates. Again, this is the first one. X coordinates differ by 2. The m coordinates in table 2, first line again, differ by 1. Table 1, the y coordinates, they differ by, now we've got to look and say, okay, they're going up by 3 plus, okay, 4 plus 4 plus 4. Yeah, we make sure. This is really important here. Check carefully to see if each value always goes up by the same amount, because it can mess you up if they don't. So the y coordinates differ by 4. Okay, n coordinates here differ by 1 plus 3 would give me 4, 4 plus 3 gives me 7, and if I stop there, I might think, oh, it's going up by 3 every time. Uh-oh. 7 plus 1 gives me 8. There's a problem. All right, so in filling this last part in, table 2, 3, 4, 1. Now, if I were to graph those, oops, what we're going to see, right, once you've graphed that, what you're going to see, and this is going to depend on the scale you use, but if we do table 1, we will get a straight line graph. Table 2, we'll get a straight line graph for a little ways. And then it'll do this. It'll kind of level. It will not dip back down. That's my inability to draw a straight line with my mouse. But it will level off or stop going up as steeply, however you'd like to state that. Over here, on the other hand, we'll get a nice, we're going to pretend that's a straight line. We'll get a nice straight line, okay? So if the difference in coordinates is the same, the relationship or the relation is, this is an important math word, it is linear. As little as that looks like the word linear, L-I-N-E-A-R, linear, even though the A sort of looks more like a fish than an A. Anyways, continuing. All right. Your turn. Show you know. Determine whether each table represents a linear relation. Explain how you know. Check each answer by graphing the ordered pairs. So give it a try. Remember that in order to have a linear relation, the difference in each set of numbers has to be the same each time. All right, so give that a try for both of them. And prove it to me with a graph. All right. And this moves us on to our next question here. Photo World charges $3 for the first enlargement and $2 for each additional enlargements. Make a table of values showing the cost in relation to the number of enlargements for 1 to 5 enlargements. Is this a linear relation? Why? What is the cost for what is the expression for the cost in relation to the number of enlargements? And then finally, what is the cost of 15 enlargements? All right, so let's give it a try here. We'll first make a table of values showing the cost in relation to the number of enlargements. So for one enlargement, what does it tell us up here? $3 for the first enlargement. $2 for each additional enlargement. So for our second enlargement, we would pay $2, but we've already paid 3. So 2 enlargements would cost us $3 plus 2 more dollars, so $5. All right, 3 enlargements would be 3 plus 5 plus 2. Sorry, try that again. Is going to be 2 more dollars than 2 enlargements, so it's going to be 7. 4 enlargements, that's going to be $9. 5 enlargements, that will be $11. Is this a linear relation? Well, remember, if it's a linear relation, each time, so the difference between all of these is 1. That's pretty easy to see, right? We can count, and so there, yeah, we're good. What about these ones here? What's the difference between here? Difference here is 2, 2, 2, 2. It is a linear relation, so yes. It's linear because the consecutive numbers in both columns are going up by the same amount each time. Doesn't have to be the same for both columns, right? This the n, sorry, I guess not column, but row. N row is going up by 1 every time. C row is going up by 2 every time, but it's that same. N is always going up by 1. C is always going up by 2. Difference between, right, and I can answer it this way too, right? The difference between consecutive numbers of enlargements is 1, okay? Consecutive costs differ by 2. Since they always differ by the same amount, the relation is linear. What is the expression for the cost in relation to the number of enlargements? So here, and I'm going to have to scroll down on the way my program doesn't quite cooperate with us here. So, well, let's go here. The cost increases, you have these numbers, right? 3, 5, 7, 9, 11. Cost increases by $2 for each additional enlargement. Oops, and I should put a $sign there. All right. We're going to let n, oops, settle down, represent the number of enlargements. C will be the part of the expression for the cost. Check this expression with a value. Oh, expression for the cost, sorry. Let's try that again. I made this simpler in the end and with more steps, which then made the whole thing take longer. So my apologies. Cost increases by, again, $2 for each additional enlargement. Let n represent the number of enlargements. All right. The cost is going to be, we might think, okay, so 2n will be part of an expression for the cost. Check this expression with a value from the table. So if we look at the first one, right, if you go back to your table, you've got 1 enlargement costs $3. So 2 times 1 is 2. Oh, that doesn't work. So what do we have to add to it? Well, 2 times 1, oh, we can add 1. So therefore, you need to add 1 to get from your value to the correct one. Therefore, an expression for the cost would be 2 times n, 2 times the number of enlargements, plus 1. And then we can check this on the table. Let's try that for 4. Okay, so, right, on our table up here, we had a 4 on the top, and we had a 9 on the bottom. 2 times 4 is 8, plus 1 is 9. Hey, it works! Right? So an expression for the cost would be 2n plus 1. All right? Then we can substitute n equals 15 for this expression. So 2 times 15, oops, plus 1